Welcome to the second part of the optimization lesson. In this lesson, you're going to see more examples of optimization problems. The first example we're going to look at is an example that involves maximizing profit. So you operate a tour service that offers the following rates: $200 per person if 50 people go on the tour. For each additional person, up to a maximum of 80 people total, the rate per person is reduced by $2. Now there's a fixed cost of $6,000 plus $32 per person to conduct the tour. How many people does it take to maximize your profit? So let's now take a look at the solution to this problem. So the first thing that you're going to need to do is you're going to have to write a profit function. Now recall that a profit function involves a revenue function as well as a cost function. So our revenue function can be modeled with this expression. So the first part of the expression involves the amount of money that can be made per person. Okay, so this is the price for the tour. Now the second part of this expression is the number of people that book the tour. So price per person times the number of people that go on the tour is the revenue. Now, to find the profit, you have to take the revenue and subtract the cost. Now, the function for the cost is this function here. So we have a fixed cost of $6,000, and we also have this variable cost here where it's dependent on the number of people. Now the expression for the number of people is this: it's 50 plus x, where x is just the number of represents the number of additional people on top of the 50. So 50 is the minimum number that will book the tour. So 32, which is the price per person, times 50 plus x is an additional cost per person. Now simplifying this, so expanding and collecting like terms, we end up with 2,400 plus 68x minus 2x squared. So this is our simplified profit function. Now differentiating the profit function gives us 68 minus 4x, so this function here. So this is the change in the profit with respect to, in this case, with respect to x, or the number of additional people on top of the 50 people. Now, after determining the derivative, the next step is to set it equal to 0, since we are trying to find where there's a tangent to the curve that is horizontal, so when the derivative is 0. And so solving for x here, after setting the derivative equal to 0, we get that x is equal to 17. So the number of people that would go on the tour, and that would result in a maximum profit, would be 67. Now another thing that we can do is we can test to make sure, or just we want to check that this truly is a maximum. And the way we do that is we can find the second derivative. In this case, the second derivative is just -4. Now the second derivative is always concave down because it's negative, so it's a negative function. So for all values of x, thus there is a max at x is equal to 17. So this truly is a maximum value. So the last thing that you would need to do is answer the question, right? And the question here is, how many people does it take to maximize your profit? So it takes 67 people to maximize the profit in this case. All right, let's now take a look at another problem. So this problem involves finding the area of a rectangle. So we're asked to find the area of the largest rectangle that can be inscribed, so that means put in or fit in a right triangle with legs adjacent to the right angle of lengths 5 centimeters and 12 centimeters. The two sides of the rectangle lie along the legs. So this is what the sketch looks like here. We have a rectangle, and then here's a triangle. And what I did is I've positioned everything on the Cartesian plane, so in the first quadrant. Now we have a line here that is part of the triangle, and this line is the hypotenuse of the right triangle. Now when we look at the sides of this triangle, I've denoted this length as x and this width, in this case, as y. Now there's a point on this line, and I've denoted this point with the variables x and y. Now, knowing that this length of the triangle is 5 and then this length is 12, it is possible for me to find the equation of this line that represents the hypotenuse. And so the equation of the line is y is equal to negative 5 over 12. So the rise in this case is negative 5 and the run is 12. So the slope is negative 5 over 12. The y-intercept is 5. Okay, so this is just an equation in y equals mx plus b form. Now the area of this rectangle that is inscribed in this triangle can be represented or modeled with this function here. So a is equal to x times y. And now since this point here that is on the rectangle kind of moves along this line here where the hypotenuse is, that means that I can take my area function that contains x and y, and I can replace y with the equation of the line. Okay? Because the points of this rectangle, the top right point, has to be on this line. And so for the area function, I end up getting x times negative 5 over 12x plus 5. And then all I do is I multiply both terms inside by x. So I'm distributing here to get negative 5 over 12x squared plus 5x. After finding the derivative in terms of x, the next step is to set it equal to 0. Okay, so the derivative here for the area function is negative 5 over 6x plus 5. So in order to find this derivative, I just used the power rule. So setting the derivative equal to 0, we end up getting x is equal to 6. And then we were interested in finding the area of the rectangle. So in order to find the area, we have to use the area function that we got here in terms of x. So substituting 6 into the area function, we end up getting 15 centimeters squared, or square centimeters. Now, to make sure that this truly is a maximum, one way is to find the second derivative, and then you want to see the sign of the second derivative when x is equal to 6. Now, when finding the second derivative of this function is just negative 5 over 6, which is always negative. So since the second derivative is negative for all x, there has to be a maximum at x is equal to 6 because the tangent to the function is horizontal. So we can conclude that the area of the largest rectangle that can be inscribed is 15 square centimeters. Now let's take a look at one more problem. So a rectangle is inscribed in a circle modeled by x squared plus y squared is equal to 9. Find the dimensions of the rectangle with the maximum area. Now this is a sketch of the situation. So we have a circle with a radius of 3. And in that circle, inscribed inside of it, is a rectangle. Okay, so a rectangle fits into the circle. And so what I did here is I labeled this side of the rectangle as x, and I labeled this side of the rectangle as y. And the hypotenuse of this right triangle is 6, because the radius is 3 here and 3 here. And so I have, so one of my equations is x squared plus y squared is equal to 6 squared. So that's the Pythagorean theorem for this right triangle over here. And to find the area of the rectangle that is in here, I would just have to take x and multiply it by y. So area is equal to x times y. And so now, in order to find the maximum area, I need the area function to be in terms of just one variable. And so to do that, I isolate for y in this equation here, in x squared plus y squared equals 36, giving me y is equal to the square root of 36 minus x squared. I ignore the negative root in this case because y cannot be a negative value since it's a length. And so substituting in for y, the area function in terms of x is x times the square root of 36 minus x squared. Now, to make it easier to differentiate, what I do here is I take the x inside the square root. In order to do that, I square the x when I'm taking it into the root, because the opposite operation would be if I took the square root of this x squared, I would just end up getting x. Then I take the x squared, I multiply it in, I distribute it, and I end up getting 36x squared minus x to the power of 4 inside the square root. After getting after simplifying the area function, I then go on to differentiating. So I use the power rule as well as the chain rule. Simplifying ends up giving us 72x minus 4x cubed over the square root of 36x squared minus x to the power of 4. Just like with all optimization questions, once you have the derivative, you set it equal to 0 in order to find critical values, to find where the tangent is horizontal to the curve. And so when setting the derivative equal to 0, I'm just setting the numerator equal to 0, because when I set this derivative to 0, I first have to multiply both sides by the denominator, so the denominator just ends up becoming 0 because it gets multiplied by 0. Now factoring the numerator here of the derivative, I end up with negative 4x times x squared minus 18. And the critical values that I get here are plus or minus 3 root 2. Now, I exclude the negative value because x cannot be negative here since it's a length. And all that's left for me to do is to find the y value, to find the y dimension of this rectangle. So taking my equation for the y, I substitute 3 root 2 into it, and I end up getting plus or minus 3 root 2. Now the negative here doesn't matter, and for that reason we would have to exclude it. And so in the end, we can conclude that the dimensions of the rectangle with maximum area is 3 root 2 by 3 root 2 units. So we're not given any units in the question, so we just have to assume that we just have regular units. So we're not, the question is not specifying centimeters or meters or anything like that. And so that would be how you would solve a problem like this. Now in the next lesson, in the next part of the optimization lesson, you're going to see more examples of optimization problems. Thank you for watching, and until next time.